I want you to imagine the entire Earth, like every square inch of the oceans, the continents, the ice
Oh,
caps.
the whole system.
Yeah, the whole thing. Now imagine that the fundamental energy imbalance of our entire planet, the actual mathematical difference between the heat coming in from the sun and the heat escaping back into space has, well, it's essentially doubled.
Which is just a staggering thought on a planetary scale.
It is. And because of that doubling, there is currently this massive, almost invisible freight train of boiling heat hiding exactly 300 meters below the surface of the Pacific Ocean.
Yeah, and it's not staying put.
Exactly. It's locked in, it is moving, and it is going to completely rewrite global temperature records in 2026 and 2027.
I mean, we are looking at a planetary scale energy release here. This is a physical reality that alters the atmospheric physics over every single continent.
Yeah.
It's fundamentally rewiring the baseline of, what we even consider normal weather anymore.
Yeah. Welcome to Meteorology Matters, the podcast that dives deep into the science, chaos, and stories behind the weather that shapes our world. This show was created by meteorologist Rob Jones. Now, let's get into today's episode of Meteorology Matters.
The data coming in right now is just, it's forcing us to reevaluate our entire understanding of modern atmospheric science. I mean, we are watching a masterclass in planetary mechanics unfold in real time.
Yeah. And so our mission today is to break down the development of a massive El Niño, but, simply saying the ocean is getting warmer, it doesn't even begin to cover the reality of what the research is showing us.
So it's way more complex than that.
Right. We need to explore how a violently shifting climate baseline is actively amplifying the power of this phenomenon. Like, we are going to trace mechanically how this hidden ocean heat acts as a global domino effect, literally rewiring weather patterns from the Amazon rainforest all the way up to the Gulf of Mexico.
To really grasp the scale of what is developing in the Pacific right now, we first have to establish the starting line. Atmospheric physics relies really heavily on a metric called Earth's energy imbalance, or EEI.
Okay.
And this is the ultimate non-negotiable driver of global temperature change.
So Earth's energy imbalance is essentially like a planetary ledger,
Yeah,
right?
that's a good way to put it.
Heat comes in from the sun in the form of shortwave radiation, and then heat radiates back out into space as longwave radiation. And, if those two numbers are equal, the planet's temperature basically stays flat.
Exactly. But if the incoming solar radiation exceeds the outgoing thermal radiation, the planet accumulates energy, and we measure this in watts per square meter.
Okay.
So from the year 2000 all the way through 2014, the research shows that Earth's energy imbalance was relatively stable. It was hovering right around 0.6 watts per square meter.
Which means for every single square meter of the Earth's surface, from the middle of the Sahara Desert to the ice sheets of Antarctica, there was an extra 0.6 watts of energy being absorbed rather than escaping.
Yeah.
And it sounds like, a tiny fraction of a light bulb. But when you multiply that by the surface area of an entire planet, the sheer volume of trapped thermal energy is just astronomical.
It's massive. And the historical stability of that number is what makes the current data so alarming. Over just a 13-month period, spanning from January 2025 to January 2026, that imbalance didn't just experience a slight statistical tick upward.
It skyrocketed.
It violently spiked. It jumped to 1.5 watts per square meter.
Wow, so that is more than double the baseline rate of heat retention in just over a year.
Yep.
The planet is fundamentally trapping twice as much heat right now as it did a decade ago. And, diving into the research on why this sudden spike occurred reveals one of the most counterintuitive, almost paradoxical elements of human industry.
It really is. Wow.
It comes down to microscopic particles of air pollution.
Right, we were talking about aerosols here. When we discuss fossil fuel emissions, the focus is almost exclusively on carbon dioxide, the invisible gas that traps long-wave radiation.
Sure, the greenhouse effect.
Exactly. But industrialization, particularly coal burning and heavy shipping, also pumps massive quantities of sulfur dioxide and soot into the lower atmosphere.
And these aerosols, they behave entirely differently than greenhouse gases, right?
Completely differently.
Instead of trapping heat, they act as a physical barrier. Like microscopic sulfate particles scatter and reflect incoming shortwave solar radiation right back into space before it can ever reach the surface.
Yeah, they literally block the sun.
And beyond that, they interact with the hydrological cycle. I was reading how they act as cloud condensation nuclei, artificially seeding clouds over the oceans, making those clouds denser, brighter, and just highly reflective.
Exactly. The physical mechanism you're describing created what is essentially an unintentional geoengineering effect. We inadvertently shrouded the northern hemisphere in an industrial sunshade. This thick layer of atmospheric grime artificially cooled the planet, actively masking the intense warming effect that our simultaneous carbon dioxide emissions were generating.
So we basically built a giant pollution umbrella.
That's exactly what it was.
For a century, the smog was acting as a shield against the sun. But, I mean, the trade-off was horrific air quality. We were looking at acid rain decimating forests, soaring rates of asthma, and critical respiratory crises in major industrial hubs.
Right, the health and environmental toll was just unsustainable. So in response, global environmental agencies, beginning with the formation of the EPA in the United States and spreading globally, instituted really aggressive regulations to scrub these pollutants from our exhaust.
And we succeeded.
We did.
The research highlights a massive, highly successful global reduction in these specific cooling aerosols. China, for example, modernized its power grids and cracked down on industrial smog, reducing its aerosol emissions by a staggering 75% since they peaked around 2006.
And the maritime shipping industry followed suit. International regulations recently forced global cargo fleets to switch away from sulfur-heavy bunker fuel.
Oh, right.
Yeah, so almost overnight, the vast artificial cloud tracks that used to follow cargo ships across the Pacific and Atlantic Oceans just vanished. We literally removed the sulfur from the exhaust.
So we did the right thing for human lungs. We cleaned the air.
Yep.
But by doing so, we abruptly closed the pollution umbrella. The smog cleared, and the planet was suddenly subjected to the full, unmitigated, brutal force of the sun. The carbon dioxide had been pushing the temperature up all along, but the aerosols were pushing back.
Exactly.
Now the resistance is gone.
And the removal of that resistance exposed a catastrophic miscalculation in legacy climate models. Early intergovernmental panels attempted to determine a metric known as climate sensitivity.
Okay, what is that exactly?
They needed to know the exact temperature increase that would result from doubling the concentration of atmospheric CO2.
Right, but they were calculating that sensitivity while the umbrella was still open. They observed the historical temperature rise, saw that it was relatively gradual, and concluded that a doubling of CO2 would only result in about 3 degrees Celsius of warming. They assumed the atmosphere was somewhat resilient.
Yeah, their mathematical models failed to fully isolate the artificial cooling effect of the aerosols. So now that the air is clearing, modern physics-based data reveals the terrifying reality.
The sensitivity is much higher.
Significantly higher. The research now proves that a doubling of CO2 will likely result in 4 to 5 degrees Celsius of warming. The atmosphere is hyperreactive to trapped heat.
So our fundamental baseline has shifted. The Earth is currently retaining double the heat it used to, and the atmosphere is far more sensitive to that heat than we ever modeled.
Right.
We take this supercharged, boiling baseline, and we trigger the single most powerful natural heat-releasing mechanism on the planet. Well, my math gets terrifying.
Which brings us to the anatomy of the Super El Niño currently developing in the Pacific Ocean. The latest models running out of the European weather forecast centers indicate a thermal anomaly that just defies recent historical precedent.
Let's look at those numbers. The modeling suggests that water temperatures in the central equatorial Pacific could hit 3.0 degrees Celsius. That's 5.4 degrees Fahrenheit above average by late 2026.
Yes.
I mean, for an area of deep ocean larger than the continental United States to sit 3 degrees above normal, the sheer volume of joules required to sustain that is difficult to even comprehend.
It is. If the anomaly reaches that 3.0 degree threshold, it won't just be an unusual weather year. It will rival or surpass the most devastating natural climate events in recorded history, specifically the catastrophic events of 1877 and the massive release we saw in 2015.
But a thermal mass of that magnitude doesn't just spontaneously generate. It requires a mechanical trigger. How does an anomaly this massive actually begin?
It begins in the atmosphere, specifically over the western Pacific near Indonesia. We observed a rare triplet cyclone pattern. The triplet cyclone. Yeah. 3 distinct cyclonic systems aligned perfectly, generating a violently anomalous burst of westerly wind right along the equator.
Normally, the trade winds blow steadily from east to west, right? Pushing warm surface water toward Asia and allowing cold, nutrient-rich water to upwell off the coast of South America.
Normally, yes.
But this triplet cyclone effectively reversed the fan.
Exactly. The reversal of that wind field applies immense friction to the ocean surface. It physically suppresses the thermocline, that's the boundary layer, between warm surface water and the freezing abyss below.
Okay.
This burst of westerly wind acted like a colossal atmospheric plow, gathering the massive pool of warm water normally stationed near Indonesia and violently shoving it eastward across the Pacific Basin.
I do have to push back a little here, though. I was looking at the recent buoy data from NOAA, and the surface temperatures in the Nino 3.4 region seem incredibly volatile right now.
Oh, they are.
We had a cold front push through a few weeks ago, and the surface anomaly actually dropped temporarily. So how can the research confidently predict a global record-shattering event 2 years out when the surface data is jumping around like that?
Relying on surface temperatures is a classic analytical trap. The Nino 3.4 surface index is subject to constant weather noise.
Noise, like what?
Like a localized storm can churn up cold water, or a passing cloud deck can block the sun and drop the temperature. If you only look at the skin of the ocean, you miss the actual mechanism driving the event.
So the true thermodynamic engine isn't at the surface. Where is the research looking to find this level of certainty?
We look at the 300-meter secret.
Ah,
The only reliable predictor of a Super El Niño is the total heat content trapped in the upper 300 meters of the Pacific Ocean. Deepwater sensors deployed across the equatorial Pacific track the formation of Kelvin waves.
Kelvin waves.
Yeah, these are massive subsurface pulses of warm water that travel eastward, totally immune to the weather fluctuations on the surface.
Wow, so while the surface temperatures are jumping around, there is a slow-moving, unstoppable freight train of boiling water moving through the dark 300 meters deep.
Precisely. And the deep water temperature readings inside this advancing wave are staggering. Sensors have recorded pockets of water reaching an incredible 7 degrees Celsius or 12.6 degrees Fahrenheit above normal.
That's insane.
By early April of 2026, the average heat anomaly for the entire upper 300 meters of the equatorial Pacific had already reached plus 1.6 degrees Celsius.
So that wave is just hurtling toward the coast of South America.
Yes, it is.
And when it finally hits the continental shelf, that deep, dense heat has nowhere to go but up. It breaches the surface and begins violently expelling thermal energy into the atmosphere.
Right.
This is where the local ocean anomaly becomes a global weather engine. Let's mechanically trace how this expelled heat disrupts every continent, starting with, well, the amplification factor.
Yeah, before we map the regional impacts, we have to apply the foundational rule of this new era of meteorology. These anomalies are now interacting with an inherently warmer base atmosphere.
And that invokes the Clausius-Clapeyron relation, right? The physical law stating that a warmer atmosphere expands and can hold exponentially more water vapor.
Exactly. For every single degree Celsius the atmosphere warms, its capacity to hold moisture increases by roughly 7%.
7%.
Yep. So when atmospheric circulation patterns align to produce rain, the resulting downpours are devastatingly heavy because the bucket in the sky is 7% larger.
But the atmosphere is a giant sponge. When it isn't wringing that water out as rain, a warmer sky requires more water to reach saturation.
Right, it's a two-way street.
So it relentlessly evaporates moisture out of the soil, the lakes, the forests. It creates this terrifying duality. The rains become catastrophic floods, and the dry periods become flash droughts.
South America represents ground zero for this duality. When the ocean heat alters the Walker circulation, the massive loop of air flowing across the tropics, the continent physically splits in its meteorological response.
How so?
Well, in the Amazon basin, the shifting atmospheric pressure creates widespread subsidence or sinking air, which aggressively suppresses rainfall.
We've tracked the data on this during recent cycles, and the hydrological collapse is total. Evapotranspiration, the process where trees basically sweat moisture back into the air to create their own rain, halts entirely.
Just shuts down.
Rivers in the Amazon drop to 120-year lows. The primary arteries of the most biodiverse ecosystem on the planet literally dry into cracked mud.
And the vegetation desiccates, turning the landscape into a tinderbox. The destruction is particularly acute in the Pantanal wetlands, the largest tropical wetland system on Earth.
Yeah, I've seen the footage.
Driven by this supercharged evaporation, we see extreme, uncontrollable wildfires sweeping across ecosystems that are normally submerged under feet of water.
But that moisture hasn't vanished from the planet, right? It's simply been displaced. Because when you look further south, at southern Brazil, you see the exact opposite extreme.
Right. The disrupted atmospheric currents act as a conduit, funneling that excess tropical moisture southward. The supersaturated air slams into frontal boundaries over southern Brazil.
And because of that Clausius-Clapeyron amplification.
Exactly. Regions like the state of Rio Grande do Sul don't just experience heavy rain. They receive months' worth of precipitation in a matter of days. The resulting floods displace 500,000 people at a time, entirely reshaping the geography of the region.
And that massive displacement of moisture doesn't just stop at the Atlantic Ocean. I mean, the atmosphere is a globally connected closed system.
Totally.
When the circulation shifts to dump water over the Americas, it radically alters the trade winds across the Atlantic and the Indian Ocean, which brings us to the devastating reality for Africa.
Africa experiences a similar latitudinal split. The shifting global pressure systems cause the Intertropical Convergence Zone, the band of heavy rain that normally waters the tropics, to drift anomalously.
Okay, so it moves out of place.
Yeah. And consequently, the Sahel region, situated just south of the Sahara Desert alongside the entirety of southern Africa, experiences a severe suppression of their traditional rainy seasons.
We're looking at regions where subsistence agriculture relies entirely on a brief, predictable window of seasonal rain.
It's their lifeline.
The research shows that during previous anomalies of this magnitude, the failure of those rains caused crop yields in southern Africa to plummet by a staggering 2/3. It engineers an immediate sweeping crisis of food security.
Conversely, the physics over the Indian Ocean dictate a radically different outcome for East Africa. The altered atmospheric circulation weakens the normal winds that push surface water away from the continent.
So the water piles up.
Yes, a dynamic known as a positive Indian Ocean dipole often sets in, driving unimaginably warm, moist air directly onshore.
So the Horn of Africa and nations like Kenya and Somalia just get battered by an unrelenting deluge. The soil cannot absorb the influx, resulting in massive landslides and catastrophic flooding.
It's devastating.
But it's not just the physical destruction of the water, right? There's a biological chain reaction.
Absolutely. The standing water left in the wake of the floods, combined with the anomalously high temperatures, engineers the absolute perfect breeding ecology for mosquitoes.
Oh, wow.
The research extensively documents that these specific meteorological setups are directly followed by tragic, explosive outbreaks of malaria and other vector-borne pathogens, devastating populations that are already displaced by the flooding.
It's a really sobering realization of how deeply entangled these systems are. Like a Kelvin wave rolling 300 meters below the Pacific directly correlates to a malaria epidemic in East Africa 2 years later.
It's all connected.
Let's trace this mechanism further east into Asia.
The overarching influence of this anomaly across South and Southeast Asia is intense, relentless heat. The immense descending air masses associated with the disrupted Walker circulation create high-pressure domes that stubbornly delay or entirely suppress the vital monsoon rains.
Right.
India and Southeast Asia face withering agricultural droughts and wet bulb temperatures that
Right.
push the very limits of human survivability.
I want to dig into the mechanics of Asia a bit deeper, though, because deducing the impact on China isn't as straightforward.
It isn't.
When we review historical data of these massive climate events, China is frequently devastated by monumental flooding, not just the drought you'd expect from a suppressed monsoon. Why does the mechanism flip so violently over the Chinese mainland?
That brings us to a highly volatile atmospheric mechanism known as the La Nina whiplash.
Because these massive anomalies rarely just fade away peacefully, do they? A Super El Niño represents a massive imbalance, and the Earth's system often overcorrects, swinging the pendulum violently in the opposite direction.
Precisely. The opposite dynamic takes hold. The warm water dissipates, and incredibly cold water from the deep ocean violently upwells to the surface, triggering a rapid onset La Nina.
Okay.
It is actually not the peak of the warm phase that poses the greatest existential threat to China, but the speed and violence of its collapse.
How does that transition mathematically trigger the floods?
Well, when the equatorial Pacific rapidly cools, it fundamentally restructures the atmospheric pressure gradients over the western Pacific basin. It generates a sprawling, immovable high-pressure system parked over the ocean.
And in the northern hemisphere, air flows clockwise around high pressure.
Right, so the western edge of that high-pressure system acts like a massive atmospheric fire hose, continuously scooping up deep tropical moisture from the ocean and ramming it straight into the Chinese mainland.
It creates an unyielding conveyor belt of water.
Exactly, and because the high-pressure system is so stubborn, the frontal boundaries stall out over land. We saw this exact mechanism play out during the La Nina whiplash, following the historic 1997 warm phase.
The 1998 floods.
Yes. The relentless moisture feed triggered the infamous 1998 Yangtze River floods. We're talking about 2 continuous months of torrential rain that overtopped dams, killed over 3,000 people, and caused catastrophic economic ruin.
So the atmosphere's attempt to return to equilibrium can be deadlier than the original disruption.
Often it is.
It is staggering to visualize this continuous chain of global devastation. But I want to pull the focus back from the Yangtze and the Amazon. Let's bring this directly to North America. We need to mechanically map how this ocean heat reshapes the atmosphere over the United States and the Gulf of Mexico.
The primary mechanism driving North American weather during these events is the manipulation of the subtropical jet stream. Normally, the northern polar jet stream dictates the winter weather across the U.S. and Canada, bringing cold fronts down from the Arctic.
But the thermal energy erupting out of the Pacific Ocean completely overwrites the normal atmospheric hierarchy.
It does. The sheer volume of heat released into the tropics forces the air to rise violently. As that air hits the top of the troposphere and spreads poleward, the Earth's rotation forces it to accelerate, injecting massive amounts of momentum into the subtropical jet stream.
It takes a relatively weak upper-level wind pattern and supercharges it into an unyielding atmospheric river.
Exactly. The subtropical jet drops anomalously far south and locks into place. It acts as a high-speed conveyor belt, continuously scooping up dense Pacific moisture, dragging it across northern Mexico, pulling additional humidity straight out of the Gulf of Mexico, and painting the entire southern United States from Texas straight across to Florida in heavy, continuous precipitation.
The result is a total washout of a winter. Southern states that normally experience mild, dry winters are suddenly hit with relentless drought-busting rains, massive, severe thunderstorm outbreaks, and significantly below-average temperatures due to the constant cloud cover blocking the sun.
Meanwhile, the northern U.S. and Canada experience the exact opposite.
Right, they dry out.
Because the primary storm track is forced so far south, the northern latitudes are starved of moisture and isolated from the typical Arctic outbreaks. They experience anomalously warm, startlingly dry winters, severely impacting snowpack and winter agriculture.
Knowing that the subtropical jet stream acts as a fire hose pointed at the south, it's easy to assume the entire year is a washout. Like if I'm planning a summer vacation to Florida or the Gulf of Mexico during a developing anomaly, I'd assume I'm going to be rained out every single day.
The research reveals a profound seasonal misconception regarding that exact assumption.
Oh, really?
Yeah. The supercharged subtropical jet stream is strictly a winter and early spring mechanism. As the Earth's axial tilt shifts the seasons into summer, the atmospheric dynamics undergo a total reversal.
So the fire hose shuts off in the summer.
It does more than shut off. The broader global circulation actually suppresses rainfall along the southern coast. The massive thunderstorms over the Pacific push air high into the atmosphere. That air has to come down somewhere.
And it comes down over the U.S.
It descends over the Caribbean and the Gulf of Mexico.
And descending air is the enemy of rain.
Exactly.
For a summer thunderstorm to form, you need convection. You need warm, moist air at the surface to rise rapidly, cool, and condense. But if the entire atmospheric column is slowly sinking, it acts like a lid on a boiling pot. The air can't rise.
Therefore, convection is actively suppressed. The data conclusively shows that during the summer months of these massive events, the Florida Peninsula sees negligible rainfall impact, and the coastal communities along the Gulf of Mexico from Texas through the Florida Panhandle are actually measurably drier and sunnier than a normal summer.
That is wildly counterintuitive. The wettest winter leads directly into a drier summer.
It's all about the seasonal shift in the atmospheric mechanics.
But that sinking air, that suppressed convection over the Gulf of Mexico and the Caribbean, leads us directly into the most critical question for the coastal United States. If convection is suppressed and the atmosphere is stable, does that mean the Atlantic hurricane season is effectively canceled?
This brings us to the hurricane paradox. From a pure, generalized statistical standpoint, a Super El Niño significantly suppresses tropical cyclone development in the Atlantic basin.
Let's break down the physical forces driving that suppression. Because the layman assumption is, the planet is hotter, the oceans are boiling, therefore hurricanes must be getting infinitely stronger and more frequent.
Right. That's what everyone assumes.
But the mechanics of a tropical cyclone are incredibly fragile.
Very fragile. A hurricane is essentially a massive thermodynamic engine. It relies on a delicate, unobstructed vertical alignment to function.
I always picture a developing hurricane as a vertical tower of children's building blocks. For the storm to intensify, that tower needs to be perfectly stacked from the surface of the ocean all the way up to the stratosphere.
That's a great analogy.
It has to act as a pristine chimney, pulling hot air from the ocean surface and venting it out the very top of the storm.
That is the exact mechanical requirement. And during these events, the atmospheric disruption over the Pacific ensures that the chimney cannot stay vertically aligned.
Because of the shear.
Yes, the intense thunderstorms over the Pacific push enormous volumes of air upward. When that air hits the top of the troposphere, it spreads rapidly eastward, creating incredibly fast, tearing westerly winds high above the Caribbean Sea and the Atlantic Ocean.
We call that wind shear. It acts like a giant, invisible hand sliding incredibly fast right across the top of our tower of blocks. It just violently snaps the chimney off.
The storm literally chokes on its own exhaust. Without the ability to vent air vertically, the internal pressure cannot drop. The eye wall collapses, and the thermodynamic engine stalls.
So they just get ripped apart.
Yeah, even powerful, well-organized tropical waves rolling off the coast of Africa hit this wall of high-altitude wind shear in the Caribbean and are physically torn to shreds before they can ever threaten the Gulf of Mexico.
The wind shear is the primary assassin of these storms, but the research points to a secondary, equally fascinating mechanism that shields the East Coast during these years. It involves the manipulation of the Bermuda High.
Ah, yes. The Bermuda High is a semi-permanent, sprawling, high-pressure system that resides over the central Atlantic.
Okay.
The clockwise winds rotating around this high-pressure dome act as the primary steering wheel for the entire Atlantic basin. In a normal year, the expansive Bermuda High forces developing storms to track straight west, plowing them into the Caribbean or steering them directly into the U.S. coastline.
But the global atmospheric disruption alters the topography of that pressure system.
Research demonstrates that during these anomalous years, the Bermuda High frequently weakens and physically retreats eastward. The high-pressure blockade deteriorates.
Without that invisible wall blocking their path, the storms find an escape hatch.
We call it recurving. Instead of being forced westward, the storms detect the weakness in the pressure field. They track west for a few days, slide into the trough left by the retreating Bermuda High, and hook sharply to the north, curving harmlessly out into the open waters of the northern Atlantic, completely missing the east coast.
So we have tearing wind shear decapitating the storms in the Caribbean, and a weakened Bermuda High allowing them to harmlessly recurve out to sea. It paints a picture of total safety. But I have to inject some heavy pushback here, because communicating this to the public is dangerous.
Very dangerous.
Fewer storms statistically does not mean zero danger. Chaos theory dictates that the atmosphere is never absolute.
That is the most vital caveat of this entire discussion. Equating a suppressed season with a safe season is a catastrophic failure of risk assessment. We need look no further than the data from the 2015 event to validate the chaos of the atmosphere.
Right.
The shear was immense that year, yet it still produced devastating anomalies.
The atmosphere always has loopholes. Hurricane Joaquin in 2015 is the perfect example.
Joaquin represents the ultimate failure of the safe season assumption. Despite the hostile global wind shear, the local environment over the Bahamas temporarily aligned. The shear slackened just enough for Joaquin to find a pocket of favorable upper-level winds.
And it exploded.
It rapidly intensified into a monstrous Category 4 hurricane. The steering currents collapsed and the storm stalled, sitting stationary over the central Bahamas for days, subjecting the islands to a relentless, unyielding barrage of storm surge and Category 4 winds that annihilated local infrastructure.
And it doesn't even require a major hurricane to trigger a disaster. Tropical Storm Erica formed that same year.
Erica is perhaps an even more poignant example. The wind shear we discussed did exactly what it was supposed to do. It constantly assaulted Erica, preventing it from ever achieving hurricane status. It remained a disorganized, sheared tropical storm.
But as it passed over the island of Dominica, the sheer volume of deep tropical moisture it was dragging along interacted with the mountainous topography of the island.
The mountains forced the saturated air upwards, wringing it out like a sponge. Erica unleashed an epic historic deluge of rainfall over Dominica.
It was catastrophic.
The resulting flash floods and massive mudslides wiped out entire villages, severed the island's communication and transportation networks, and set their economic development back by decades. A sheared, dying tropical storm inflicted absolute ruin.
It is a terrifying testament to the fact that the atmospheric math may heavily favor suppression, but it only takes one rogue system finding one tiny pocket of favorable conditions to rewrite the history of a coastline.
Exactly.
Whether we are analyzing the desiccating drought in the Amazon, the displacing floods in southern Brazil, the deadly La Nina whiplash over the Yangtze River, or the rogue storms defying the wind shear, all of this immense planetary chaos is driven by one singular mechanism.
An ocean that absorbed too much heat. violently expelling that energy back into the sky.
And that heat cannot just vanish into the void. It has to be absorbed by the global atmospheric system. Which brings us to the ultimate overarching question of this analysis. After this 300-meter deep wave of thermal energy finishes violently discharging into the troposphere, where does that leave our global thermometer?
It shatters the paradigm entirely. If we trace the mathematical progression of the energy transfer, 2026 is virtually locked in to smash the global temperature records that were recently set in 2024. The thermal energy is already baked into the oceanic system. It is just a matter of physics playing out.
But the peak of the heat transfer isn't immediate, right? There is a latency period in the Earth's system.
Exactly. The atmosphere is massive, and it takes several months for the heat expelled from the equatorial Pacific to fully circulate, mix, and register across the global network of atmospheric sensors.
So the data lags.
Because of that lag, the true thermal peak will hit the following year. Current analytical models indicate a 73% probability that 2027 will become the absolute warmest year ever recorded in human history.
When you take a step back and examine the sheer geological scale of the data we are discussing, it induces a profound sense of vertigo. I mean, the past 10 years are already unequivocally the warmest on record.
Yeah, the trend is undeniable.
By the time the final data for 2026 and 2027 is compiled, paleoclimatology research suggests that the Earth will likely be warmer than it has been in at least 120,000 years, dating back to the Eemian interglacial period. We are walking into a climate baseline that modern human civilization has never experienced.
We have forcefully pushed the planetary baseline into entirely uncharted territory. And the natural meteorological cycles, rather than bringing us back to equilibrium, are now compounding and violently amplifying that new, boiling reality.
It leaves me with a philosophical puzzle to ponder as we conclude this analysis. We began this discussion by examining the aerosol paradox. We looked at how our collective, well-intentioned human effort to clean up industrial air pollution to do the right thing for our lungs, and our forests accidentally closed our cooling umbrella and drastically accelerated the planetary warming.
Yeah, an unintended consequence.
It forces you to wonder, what other invisible safety nets might exist in the chaotic, highly complex math of our atmosphere that we don't fully understand yet? What other delicate compensating mechanisms are we relying on without even knowing they are there?
It remains the ultimate looming question of atmospheric science. Every new data set proves that the deeper we look into the mechanics of the Earth, the more we realize just how precarious the balance truly is.
It is a balance we are actively watching shift in real time, and we will continue to track the data as this unprecedented anomaly unfolds. We want to thank you for joining us on this exploration of the physics driving our sky.
Yes, thank you.
If you found this discussion valuable, please take a moment to like, follow, comment, and rate the podcast. Your engagement helps us tremendously. And to stay updated on the data as this global event develops, make sure to follow Rob Jones on social media. You can find him on Instagram at @Meteorologist, on TikTok at @TV Meteorologist, and on YouTube at Rob Jones Hurricane, where you can also find the full Meteorology Matters podcast playlist.
The ocean is still holding secrets, the data will keep rolling in, and we will be here to break down the mechanics behind it.
You've been listening to Meteorology Matters, created by meteorologist Rob Jones. Thanks for listening, and remember, meteorology always matters.